Okay, so we already know enough to understand why this thing happens. So just to remind you, for those if you haven't seen it before, so if you just release the wheel, it just falls down. But if you start spinning the wheel and release it, it doesn't fall down. It just turns around that vertical axis. Now, if you rotate it, the faster. Well, it's not. It wasn't easy to see the change in the speed. So now we can see why it happens. Hala çalışıyor. So let's look at our system. We have this wheel with some moment of inertia. It is balanced from a point that is out of the wheel, and the wheel is rotating like this. So it has an, let's say it has an angular velocity in this direction. This is the direction of the angular velocity. So we can look at the rotations around this point. Well, there is a torque created by its weight for rotations around this point. So there is this weight, its weight. It creates a torque with respect to this point, and that torque, if let us just choose our coordinate axis, x, y, and z. The point of action of this weight r is equal to, let's say, some distance L times y hat direction. This is our r. F, or its weight, is equal to minus mg z hat. Omega is equal to, well, it has its magnitude. It's in the y direction, so I'm assuming that it is rotating like this. So this is the wheel. So it is rotating like this. So the right-hand rule just tells me that its angular velocity in this is in this direction. And this is my support point. This point over here. The torque acting on my system for rotations around this point is r cross f. Well, r and f, they are at 90 degrees. Well, f is the weight, so it is mgl. And the direction of the torque is, in this problem, what's the direction of the torque? This is my r vector. This is the weight inside the blackboard, which is minus x direction. Minus mgl x hat. This is the torque I have. Well, the torque creates a angular acceleration. I alpha. This is the torque created by my system. So alpha is minus mgl over I x hat. This is the direction of the torque acting on my system with respect to this point. So if my system has some initial angular velocity, omega, then it will have at some successive time, the angular velocity will be omega plus alpha dt. Omega is pointing like this. If you just look at it from the top, this is the direction of omega. This is the x direction. This is the y direction. The z direction is pointing towards you. So this is omega. Alpha is in the minus x direction. This is, let's say, d omega, the change in omega. So the omega vector should rotate around the z-axis. So this is my new omega vector. And note that omega vector, the velocity vector, angular velocity vector, and the angular acceleration vectors, they are perpendicular to each other. Well, this is just like the circular motion. Remember, in the circular motion, the velocity and acceleration, they are always perpendicular to each other. But it also means that the velocity, as my system is doing some uniform circular motion, the velocity, the speed doesn't change. Well, it will be the same thing here. The angular velocity will not change. The angular speed will not change. It will have the same angular speed. It will only change its orientation. So omega vector, under the influence of this torque, should change its direction. But if it is changing its direction, in the changing its direction, omega vector is along this axis. That is the direction of the omega vector. But we know that since the angular acceleration is in the -x direction, omega vector should change in the -x direction. But it also means that the axis should rotate in the -x direction. So if initially this is my axis, then my axis should go like this, so that I will have such an alpha vector. For such an alpha vector, my axis should go like this, not down. It should go like this. And that is what's happening. Well, I need another volunteer once more. Now, this tells me that if my system is initially rotating like this, then the whole wheel should rotate in this direction. At this orientation, it should move inside the blackboard and like this. So did anybody pay attention to which direction it rotates? So we said that, okay, so it should, if I spin it like this, it should be rotating. You go there. Okay. So if I spin it like this, it should just turn like this. That is what our derivation tells us. Let's see. It didn't work. Why not? Well, okay, sorry. Because it is rotating in the wrong direction. This is the system. The wheel is on the left, and it is rotating like this, such that no, it's rotating like this. Okay, so that the right-hand rule gives an angular velocity in that direction. Okay, so let's spin it. So what's wrong? R cross F. R cross F. It is doğru is correct. So it is rotating like this. The angular velocity is in this direction. It should rotate like this. No? Yes. It's correct. So you are saying it's because of the cord. Okay, now the cord is relaxed. It's not twisted. So it should be rotating like this. No, it's not because of the cord. So what else can we test? Oh. So, okay, what about how fast does it turn around the cord? It's angular velocity for rotations around in the xy plane. Not this rotation frequency, but this rotation frequency. Now this angle over here, d theta. d theta will be nothing but dw divided by w. That is how much it rotates. Well, dw is alpha dt divided by w. So d theta by dt is, well, alpha was rf r times f. This is the torque divided mgr. This is the torque divided by the moment of inertia w. So this is how fast it rotates in the around the vertical axis. Now, if r is larger, this tells me that it should rotate faster. This is our prediction. Well, let's try it. Volunteer. Well, before we used to put the cord just very close to the wheel. Now we will just put it almost towards the edge. Hold it tight. Bring it a bit closer. Can somebody time it? Who has a timer? No, not yet. Did you start the timer? Okay. Now. Stop. So it takes 6 seconds. Bring it closer. Start. It's much slower. So that at least we could test. The larger the r was, that is when we put it over here, increasing the distance r, its angular velocity for rotations around the vertical axis just increased. It started to rotate faster. Well, we can try w, but it's kind of hard. I mean, we did many approximations here. Now, at this point, I said that the omega is always in the axis of along the axis of rotation, along this direction. But once it starts rotating around this axis, angular velocity also gains a component in the vertical direction. So angular velocity is no longer in the direction of the axis. That will complicate the motion. But if the angular velocity along this direction is much, much larger than the angular velocity around this vertical direction, now we can just ignore that component. And that is what we have done over here. We had all assumed that omega is always along the direction of the axis. So this result is valid only if omega is large enough. If omega is not that large, then this approximation will not hold. But if omega is large, increasing omega by hand will be much more complicated. So it's hard to test this one just by hand. But at least we managed to test one of this. So this is what we have. So the discussion of the angular velocity, the torque, the derivation we had is enough to explain this phenomena. So why does it fall down if it's not rotating? Well, that's another limit. Well, one limit is if it rotates very fast, such that omega is very fast enough, then this derivation tells us that it should rotate around the vertical axis, and it allows us to calculate the angular velocity or the period for rotations around the vertical axis. The other limit, if this is not rotating, we know that it just falls down. So why does this argument break, or this argument, does it break in that case? if omega is initially 0. We don't know angular momentum. You see, the critical thing is this alpha. We had calculated that alpha should be mgl over I in the, well, it should be in the minus x direction. It should gain some angular velocity inside the blackboard. Now, if it has some initial angular velocity, the way for it to gain some angular velocity inside the blackboard is just to rotate the angular velocity vector. So if it rotates, then it gains some component inside the blackboard. But if it's not rotating, initially it has 0 angular velocity, so the only way it can gain some angular velocity in this direction is if it starts rotating around this axis. So this rotation causes it to have some angular velocity in this direction. So in both cases, that in fact, whether it is rotating or whether it is at rest, it is just trying to gain some angular velocity in this direction. But if the omega is very small, the only way for it to gain angular velocity is if it falls down like this. If it is rotating sufficiently fast, the only way would be just if it rotates like this. For somewhere in between, it will make much more complicated motion. It will just go up and down. It will be wobbly. It will be moving, rotating around the vertical axis, but at the same time falling down. Things get complicated, but at least in these two limits, when it is rotating really fast or really small, we know what it will do. Okay, just one confession. Yes. Yes, that's what they say. They always say that, well, just like if you remember our discussions about the satellites, why don't the satellites fall? And my answer was that the satellite is falling down. And whenever I ask anybody about what does this do, why doesn't this fall when you just let it go, the answer I always get is that it is falling down, but I don't understand it. That's one thing I don't understand. How come? I mean, by understanding, okay, I can do the derivations, I can use it, but if you think in terms of the point masses making this system, how come all those points, initially they are making such circular motion, when you just let it go, how does this motion arise? I have no idea. Yeah, that's a confession. I have some understanding, though. Well, by the way, you had a question to think about during the break. Well, let's continue with this one, and then we will come back to that. Yes. Let's try. If the wheel rotates in the other direction, does it make any difference? So let's see. I will rotate, spin the wheel according to me in the counterclockwise direction. So it rotates like this. Now, clockwise direction, it rotates in the other way. So you see, if W changes sign, that's what we did. If W changes sign, then d theta by dt changes sign. So it will start rotating in the other direction, yes. Yes, the rotation is not about the air friction. It has nothing to do, well, it's not like the boomerang, if that is what you had in your mind. This has nothing to do with air friction. It also works in space. In fact, it is used in spaceships. Well, it used to be. Other questions? Well, you see, if you trace the derivation, there is this torque which has to be acting on the system. So in the absence of this torque, it doesn't do anything. I mean, if you just hold it from both ends, nothing happens. If you start to try to rotate it, did anybody try to rotate it? Holding it holding it by both your hands, it's just quite easy. But if you try to rotate it, I'm not doing it. It's doing it on its own, this motion. You don't believe me? Come. Hold it. Try to rotate it. Okay. Anybody else who doesn't believe me? This wall. If you just try to rotate it, a simple rotation. That's what I'm trying to do. It just goes wild. Anybody else wants to try? He was quite suspicious. So the main claim here, if you have something that has some angular velocity, the main point, it is hard to rotate it. It tries to stay as it is. But that is something nice, especially if you are in space or in the ocean, where you don't really know which direction you are going. You would rather have something that will show you your orientation. And these things are used in ships. They used to be used in ships. Nowadays we have electronic versions because they do not change their direction so easily. Okay, so we are spinning it. Now you see, it's not turning around if I hold it symmetrically. Why? If you just look at this description, I'm holding it here, I'm holding it here. Well, you can look at it as for rotations around this axis, but then there is its weight. There's also the force from the other end. Now, when I hold it like this, both of my hands and the gravitational weight is acting a force on this thing. So the net torque on this system is 0. If I put it in space and let it just as it is, it will just stay so. Even if the ship rotates around, this will not rotate. It will stay in the air, just rotating, pointing the same direction. Yes? Well, let's see. In any of our derivations that we use that fact, whether we are on the northern hemisphere or in the southern hemisphere, no. Okay, the question is, it is easy to understand this one. So even if you think of all the points making this wheel, you know that they are all feeling a downward force, so they will all accelerate in the downward direction. Okay. Which one? Now the forces are not symmetric. Dönme diyordur. Well, the forces are not symmetric. The object is, but the forces are not. If I just leave it like this, there is a force acting from this point, and there is a force acting from this point. The forces are not symmetric, so the forces will try to rotate it. When it rotates, again, if you think of all the point masses making up this wheel, they all feel gravitational force, plus they all feel the internal forces. And the gravitational force acting on all of them is downward. So I would have expected them to fall downward, but this is what happens. Why? That I don't understand. How come from the point particle picture you can get this rotation? fall down. I mean, if you didn't know the answer, would you come up with such an explanation? Would you? I wouldn't. Let's just take 4 points. They are connected by some rigid rods, and they're just rotating like this. So there is an angular velocity in this direction. Now, if you ignore internal forces and let's just assume that they are making circular motion, initially they are all at rest. This moves with a speed v in this direction, this moves with a speed v in that direction, v and v. When you make half a turn, this, no, 1/4 of a turn, so this point just becomes this point. Now this point is moving with a velocity square root of v squared minus gr, 2gr. Just from energy conservation, it lost some of its kinetic energy is converted into potential energy. This will move downward with an force v squared plus 2gr. This will move in this direction with a speed v squared plus 2gr. And this moves with a speed v squared minus 2gr. After 1/4 of a rotation. This is what will happen, assuming there are no horizontal forces acting on my masses. Now, if you consider the motion of the center of mass, this point, the horizontal motion of this point, Vx center of mass, will be just 1/2 v squared plus 2gr plus v squared minus 2gr. Well, it will also be the its speed in the vertical direction. The y component will also be the same because you see this speed and this speed are the same. This speed and this speed are the same. So its speed in the horizontal direction and in the vertical direction will be identical. This is equal to. Now, of course, we said that this happens if the object is rotating sufficiently fast. Omega is large, so v is large. V squared, let's just take the limit that v squared is much, much larger than 2gr. The object is really rotating fast. Now, in this limit, v squared plus 2gr, 1/2. Now, by the way, this is minus because the two speeds are in the opposite direction. V squared plus 2gr, this is equal to v times 1 plus 2gr over v squared raised to the power 1/2. This is almost equal to the speed v 1 plus 1/2 2gr over v squared. This 1/2 is this 1/2 over here. And 2gr over v squared is just here. Now remember, in one of your homeworks, you were supposed to use the relation 1 plus x to the power n is approximately 1 plus n times x for x much smaller than 1. But by making this assumption, we are saying that this number here is much smaller than 1. So all this square root is approximately equal to 1 plus 1/2 this number. So the velocity of the object in the x direction, the velocity of the center of mass in the x direction will be 1/2. Well, that is the first number, v plus gr over v, minus, well, the only difference here is that this is now minus, so this will be minus over there, v minus gr over v, which will be equal to, well, these v's, they just cancel each other, and we are left with gr over v. So you see, initially, the object, the center of mass, didn't have any horizontal component. After 1/4 of a rotation, now the center of mass should have this speed, gr over v. This is the horizontal speed. Well, it also has some vertical speed. If you calculate, if you do the same derivation for the y component, you will see that this is minus gr over v. This 1 over 2. Well, it is this 1 over 2 over here. So these two masses are equal. So the velocity, the center of mass velocity is just the average of the two velocities, two speeds. Well, this is the closest explanation I have. So as the system is rotating, it's gaining, different parts are gaining speeds at different rates. So it just translates into the center of mass gaining some finite speed. Now let's come to another point related with the same question. Also related with the question that what would happen in space if you don't hold it. Now, just look at it from the top. This is my wheel. I'm looking at it from the top view. So this is the suspension point. Its weight is inside the blackboard. This is the angular speed. I hold it like this first. It is spinning. And I am holding it with both my hands. What's the acceleration of the center of mass of the system? The center of mass. Come on, this is an easy question. 0. The center of mass isn't moving. So the acceleration of the center of mass is 0. If I remove one of my hands, the center of mass starts to accelerate. Now it is this is the position of the center of mass. Let's just ignore the mass of this point. Initially it was at rest. Now the center of mass, when I release my hand, accelerates in this direction. It has a tangential acceleration in this direction at this instant. But remember, its weight is pointing inside the blackboard. So the weight cannot give such an instantaneous acceleration. So cannot give this tangential acceleration because it's not pointing in the same direction. So which force causes the center of mass to have such an acceleration? Where is the origin of that force? The weight is pointing inside the blackboard. So I'm just looking at it from the top. So this is how I am looking at it. The weight is this way, away from me. This is bird's view. No, I don't care about that. Center of mass is a point. I'm talking about that point though. And that's my question is about that point only. About the center of mass. The center of mass, the instant I release it, it has an acceleration in that direction. Because before I released it, at the moment I released it, the center of mass had 0 velocity. When I released one of my hands, the center of mass had some velocity in that direction. And the question is, what is the source of that acceleration? Because we have seen that in Newtonian mechanics, if there is acceleration, there should be some force. So here we see there is acceleration, and we had also shown that if the center of mass has some acceleration, then there should be some net external force acting on my system. So this is the question. Here, the center of mass is accelerating. This point is accelerating. So there, well, the system has a total mass, so there should be some external force acting on my system. What is that external force? What is the source of that external force? What is acting on my system which causes this force? The force is always created by some other object. Which other object is creating that force? Because of the other hand, right? So there should be a force of my hand which creates a force. Well, in fact, you had seen it. Let's just start it. I will just release it without exerting any force. So if I don't hold it, it doesn't turn around. So that's another nice thing about this thing. This force, well, you see, as it is rotating also, there was some friction which created such a force. Because even in this case, it just started rolling in that direction. That was the friction force that creates this acceleration. For it to rotate around, you see, if the center of mass starts to make circular motion, it's not enough to have tangential acceleration. I should also have some circular acceleration. So this point should hold this object. And it should also create a force in this direction. Not only the tangential acceleration, there should also be a central acceleration. A force creating the central acceleration. Now in this example, I didn't hold it. Well, its mass is quite large, so I need significant force to hold it, to rotate it. So since I didn't exert any force, it just went in that direction without making the circular motion. Any questions? Yes. No? Well, let's see. There are two forces acting on me now. If I stop here, then start moving. Well, there are many forces acting on me. There is the gravitational force. There is the forward friction force between me and the surface of the Earth. There is the drag force of the air and me, and there is no rotation. There's just linear motion. If there are two forces, you don't need to have. Well, the only thing is the net force. Well, the net force and the net torque. If the forces do not create any torque, then you don't have rotation. Any last minute questions? What was the direction of the torque? Minus x. So that is the direction of the angular acceleration. No. Well, it's just like the normal acceleration. Acceleration need not be in the direction of the velocity. I can be moving in that direction, but accelerating in that direction. And the same thing here. The angular velocity is in this direction. The angular acceleration can be in the perpendicular direction. I will not discuss any other problems. I will do a big quiz in 2 days, so I was thinking of doing a quiz, by the way. Who wants to have a quiz? Okay, you can beat her when I don't see that. Okay, so see you on Saturday.